Hello again. So this is the part 2 of what we had started on the bioceramic materials in dentistry. So bioceramics, as we know, just to recapitulate, it's an umbrella term. It encompasses many materials, types of materials which has a long development history that we will see slowly. But today, in this episode, I'll discuss about Portland cements and how this Portland cement was used in a product that we call very commonly as mineral trioxide aggregate or MTA. So the journey from Portland cement to mineral trioxide aggregate. Now the journey of the hydraulic dental materials, as we will get to know later, that bioceramic materials can also be called the hydraulic dental materials because they set and harden in the presence of moisture, which is an inherent part of our dental tissues, hard tissues. So this started with Portland cement that was invented by Joseph Astin, who named it so for its resemblance to Portland stone. In 1824, Joseph Astin, who was an English bricklayer, he patented a process what he called as a Portland cement. So to give an example of how Portland cement was used, the first great bridge built in the USA in the late 19th century was made of Portland pozzolanic cements. Modern Portland cement is made by mixing substances containing lime, silica, alumina, and iron oxide, and then heating the mixture until it almost fuses. Now, strength, durability, and reliability are unquestionable for this particular material. Now, Portland cement is a hydraulic binder. That means it sets and hardens even underwater and is the core ingredient in modern concrete and mortar. Now, the use of Portland cement was first documented in a journal, and the first user was Dr. Witte. I don't know whether the pronunciation is correct, but he was a German dentist. He documented the first known use of Portland cement as a material for filling root canals. Now, this groundbreaking but very early application of hydraulic cement, again to remind all of you, which sets in the presence of moisture, was reported in the German Quarterly for Dentistry. The work was reported in 1878 and also referenced later in 1880, marking the first time this type of hydraulic cement was used in dental literature. So it is a moisture compatible material. Dr. Witte actually he recognized the hydraulic properties of Portland cement, that is the ability to set and harden even when it is wet and in the wet conditions. So, as we were discussing, Dr. Witte recognized the hydraulic properties of Portland cement, that is the ability to set and harden even when wet, which makes it an interesting material for the wet environment of a tooth's root canal. When Portland cement is mixed with water, the components which are tricalcium and dicalcium aluminate. When Portland cement is mixed with water, the components which are tricalcium and dicalcium silicate and tricalcium aluminate undergo a hydration reaction forming calcium silicate hydrate and calcium hydroxide from the silicate reaction and ettringite and monosulfate from the interaction of aluminate in the presence of calcium sulfate that is added to the cement by the manufactured. Now, the formation of calcium hydroxide makes the use of Portland cement multifaceted, as it can be used for all the procedures where calcium hydroxide is employed. That includes the vital pulp procedures. Now, Dr. Mahmoud Torabinejad, he refined the concept to develop MTA, or mineral trioxide aggregate, which is essentially purified medical grade Portland cement mixed with bismuth oxide for radio opacity. Now, Dr. Witte had paved the path by using Portland cement in dentistry. So Dr. Torabinejad enhanced and upped the concept and developed a product that we can actually use, which is Portland cement, which is medical grade, that is the purity is high, and because in dentistry we need radio opacity, he mixed it with bismuth oxide for radio opacity in a particular proportion that we will also see. So Dr. Mahmoud Torabinejad and his co-worker Dean White, they had two US patents to their names for the same. Now, to understand bioceramic materials, it is very essential thus to understand Portland cement. So, the understanding of the materials that we collectively call bioceramics starts with understanding Portland cement. So now, the composition of Portland cement may be described by two ways. One, by the raw oxides or the chemicals, and by the complex mineral compounds, which are collectively called Bogues compounds, that are formed during heating and which dictate the cement performance. Thus, the major chemical oxides are primarily limestone that break down into other oxides, and basic raw materials for Portland cement are thus calcium oxide, silica, alumina, and iron oxide. Now, these components are appropriately proportioned to produce various types of Portland cements. Now, these are the types of Portland cements. There are basically 5 types of Portland cements. These are identified by the standard specifications promulgated by the American Society for Testing of Materials, or ASTM. Type 1 is called the normal Portland cement and is a general purpose cement suitable for all uses when the special properties of the other types of cements are not required. Portland cements are generally available than the other type of cement. For example, type 1, which is the ordinary Portland cement, is typically used in assorted construction application. In its normal applications, type 1 cement is used when the concrete is not subjected to special sulfide hazard, or where the heat generated by the hydration of the cement will not cause an objectionable rise in temperature. Such conditions are typical of the mouth, thus it does not, or the dental applications do not necessitate the use of the type 2 to type 5 of the ASTM types of Portland cements. The process of making Portland cement is well known, and it can be purchased from any number of manufacturers under various trade names. That is not a problem. But in manufacturing Portland cement, the raw materials are crushed, ground, and proportioned for the desired composition and then blended. The mixture is then fed into a rotary kiln where it is heated to temperatures of up to 1400 to 1650 degrees Celsius. In the process, the mixture is chemically converted to cement clinker, which is subsequently cooled and pulverized. A small amount of gypsum is added to the cement to control the setting time of the concrete. The resulting cement consists principally of tricalcium silicate, dicalcium silicate, tricalcium aluminate, and tetracalcium aluminoferrite. Calcium oxide is thus the principal component of Portland cement that typically comprises in excess of 60% by weight of the overall composition. Now, the tricalcium silicate, which is 50 to 70%, provides early strength. The dicalcium silicate, which is to the tune of 15 to 30%, these are the Box compounds, they provide later strength. Tricalcium aluminate to the tune of 5 to 50% causes the initial set, and tetracalcium aluminoferrite between 5 to 15% acts as a flux during manufacturing and gives the cement its color. Now, there is another component, that is the Portland cements generally have a Blaine number in the range of 3200 to 5500 centimeters square per gram or greater. Faster setting cements like that preferably utilized in the present invention by Dr. Torabinejad has a Blaine number in the range of 4000 to 5500 centimeters square per gram. The most preferable cement utilized in Torabinejad's and White's invention had a Blaine number in the range of 4500 to 4600 centimeter square per gram. Now, water is the principal reactant in the hardening reaction that offers a significant advantage over many of the filling materials commonly used by allowing the cement to set in the moist environment of the body and tooth. Portland cement hardens by reaction with water. This is known as the hydration reaction. The reactions are very complex but principally involve the reaction of tricalcium silicate and dicalcium silicate with water, Box compounds we have seen. When these compounds react with water during the hardening of the cement, the principal hydration product is tricalcium silicate hydrate. The material is colloidal gel of extremely small particles, less than even a micron. The tricalcium silicate hardens rapidly and is most responsible for the early strength of the Portland cement. The dicalcium silicate has a slower hydration reaction and is mainly responsible for strength increase beyond 1 week. Tricalcium aluminate plays a lesser role in the hardening process. It hydrates rapidly and contributes to early strength of the cement. So as we have understood now, Portland cement is not radio opaque, but a radio opaque component is added to render it radio opaque for the purpose of dental diagnostics and dental treatment. Bismuth oxide in various ratios has been found to be a suitable such compound for this purpose. Depending on the degree of radio opaqueness desired, various ratios of additive may be used, but in the formula that was used by Torabinejad and devised by him, so there 1 part of bismuth oxide was used for 4 parts of the Portland cement. So now we have understood that whatever way the Portland cement used to be, it has seen a sea change. Like up to 1970s, what we now call the as bioceramic materials were bio-inert, like alumina. But the use expanded to being bioactive, like hydroxyapatite, which is calcium phosphate that mimics mineral composition of bone. Now, what happened is in the 1980s and 1990s, bioglass revolutionized the field of regeneration by the ability to form chemical bond and release therapeutic ions. What Dr. Mahmoud Torabinejad did was at Loma Linda University, he along with his co-inventor Dean White obtained the 2 US patents as we have already seen, and these were actually products that could be applied by the dentists. He called it mineral trioxide aggregate, but in the truest sense, it is neither an aggregate nor an oxide. Why it was named so is probably little debatable, but it was their invention and they named it so. In the next episode, we will see what is actually meant by the term aggregate when it comes to Portland cement, and why the term aggregate might be little misfit when we talk about MTA. MTA was first described in the scientific literature in 1993, and as an aggregate of mineral oxide added to trioxide. The types of materials which have been suggested as retrofilling materials, and thus the journey that started with Portland cement ended as a product in in the form of MTA, and then there were so many variations and applications of these bioceramic materials. So we have to understand that this is a journey, a process which starts with innovation, adaptation to what is required for dentistry and our use, and then we make progress by understanding the limitation of each material, because till date there is no material which is actually very perfect and very one size fits all material which can be used in dentistry. So this is all about the Portland cement and how Portland cement was used as the mother material, why it was used, and how a little bit of how it came to be transformed into a material that we use very commonly nowadays, that is MTA. In the next episode, we will learn and discuss in depth about MTA as a material itself. Thank you very much.